So, Vanakkam, we will continue our lecture on engineering seismology. So, we have been discussing about the frequency domain parameters. We told that the frequency domain parameters are highly useful for the simulation of ground motions. Okay, so particularly to get a source, path, and then the site. Okay, variation which with attenuation is a function of frequency. These values are changes. So, we discussed about the corner and cutoff frequencies. So, we have seen that the corner frequency is basically inversely proportional to the cube root of the seismic moment. So, depends upon the seismic moment means actually the seismic moment is function of the magnitude. So, depends upon the magnitude of earthquake, basically the corner frequency keep changing. Okay. So, this is basically a corner frequency, so which is inversely proportional to the cubic root moment of the seismic moment. So, this is the cutoff frequency. So, this is basically constant for the geographical region. Okay. So, this is the F max. Okay. So, this is basically different earthquake recorded data. So, how your corner frequency changes. You can see the lower magnitude to higher magnitude, how this changes, which is basically the function of seismic moment in turn is the seismic magnitude. So, we also talk about the predominant frequency and all those things. So, today class, so we will be seeing a simple simulation of ground motion theoretical models and source mechanism. So, what is mean by the source mechanism? Okay. So, the source mechanism is basically describe what type of fault it is and what type of the force is actually radiated from the earthquake source or released by the earthquake. It is a compression or tension force in predominantly we will describe. Okay. So, if you look at earthquake data, okay, so which we discussed during our fault description also, we have seen normal fault, reverse fault and transfer fault. We have seen that the normal fault generally compression force is generated. So, reverse fault generally the tensile force is generated. So, the shear force is generated under transfer fault. Okay, that is what we have seen. So, we also seen that the waves what you are getting, basically the waves what you are getting. Okay, so like this. Okay, so these waves and then so the same earthquake another place may record like this. So, we have seen that the ground push and pull. Okay, the push basically is the compression indicate a normal fault. So, the push, okay, so the dilation, okay, so dilation indicate a tension force. So, generally occurs on reverse fault. So, how it happens? So, we also described that in order to identify a particular ground motion is basically a earthquake or blasting, okay, in the rock. So, we have noticed that so most of the blasting happens in the smaller area. So, where you will have the push up all the record. So, you will have the push up all the record in all the direction, that is what we have seen in the the artificial blasting or artificial earthquake. So, in the natural earthquake it may not be like that, since it is happening with the rupturing up, like for example this is the fault. So, you will get rupture at one place is larger, one place is higher. So, then like this so depends upon the where the seismic instrument, okay, so where the seismic instrument located. So, you will get tension or compression or tension. So, describing this tension compression combination what happens at source is called as a source mechanism. So, when I talk about source mechanism, I also need to explore, like most of you might have went to beach. Okay, so I don't know how many of you beach you play a ball over a beach, but the beach whatever ball you are using to play is completely different from the ball which you play in the normal ground or football ground or volleyball ground. So, I don't know how many of you noticed that. So, why it is so? Okay. So, the ball which specifically used in the beach is called as a beach ball. Okay. So, the source mechanism, the combination of tension and the compression, okay, forces described as a ball, okay, that ball is basically called as a beach ball or source mechanism diagram. So, today we are going to discuss in detail about how to get the source mechanism at a particular place, okay, due to particular earthquake. So, the P wave will detected surface as either a push or pull. Suppose the first of the source of record P wave in the small explosion at a point of earth some distance from the seismogram. So, then the P wave to be generated would be like a air balloon into balloon. So, push outward a spherical surface wave, that is what we have seen, that when this explosion comes you will get a compressional wave. Seismogram would detect P wave as a push upward at the ground, the upward movement is referred as a compression. So, the P wave directions will be recorded as a simple pattern of the earth's surface depending upon the direction of the they first left in the source or fault. Okay. Two type of seismological beach balls are used, when the colored beach ball and black and white beach ball. So, as I told you that the beach ball is different from the your regular football and volleyball. So, your regular football, volleyball may have the unique color. Okay. So, it is the color will be almost similar with some kind of design. Okay. But a beach ball is the ball which is described in the color pattern. Okay. So, the color pattern the ball described. Moreover, the other football and volleyball basically it has a outer cover, inside there is a air balloon, a tube where it is compressed air will be there inside. So, even sometime the outer damages you still the ball will usable. But in beach ball basically this is a plastic ball colored on different colors, okay, which is a contrast attractive colors. Okay. So, the attractive colors means you can easily identify the color, okay, that kind of color ball. Why that kind of color ball which is made up of like the plastic, why? Because beach generally you will have the sand. If you have the rough surface like football or volleyball, so it will stick on the ball. You cannot use those balls in the beach, as you know that beach sand is dry as well as wet at some portion. So, you cannot use a regular ball. So, that is why these plastic balls it does not stick mud into the ball, that is the one thing. Second, as you know that the beach you will always have the good amount of sunlight. So, the uniform color ball will be difficult to identify the ball is missing. So, but if it is a colored pattern it is very easy to identify, that is why beach balls are the unique. So, you can see whenever next time when you watch any kind of beach play, you can see that most of the western country people they use this kind of ball. So, India I am not very sure people used to play ball in beach and all, particularly these colored pattern balls are familiar, but now you can Google it and find out how the beach ball are the. So, here a beach ball will be expressed in the two pattern black and white, one shows a compression, one shows a tension. So, since it has a pattern of color which is called as a beach ball, which is a source mechanism. So, if you look at this image carefully, this is a sphere of the globe. So, where earthquakes are occurring. So, then these earthquakes are recorded at a different station. As I told you that you need a 3 minimum station to find out the location of the earthquake. So, not only 3, there will be large number of stations it will be recorded. So, depends upon the what energy released at this point. So, a station will expect a compression and a tension. Okay. So, tension is called as a dilation, compression is called as a. So, here the compression is represented as a positive, tension is represented as a negative. So, you can project that and make it as a circle. You can see this is a circle. So, basically in the circle you can project. So, and then plot wherever you have a tension, wherever you have the compression. So, after plotting that you try to identify that area covered by the tension and this one, then it gives a diagram like this, a beach ball in the plan view. So, that is called as a source mechanism. So, this is a typically source mechanism for the strike fault plane n north degree east and dip. So, this will also give you the dip and strike angle, how much the compression tension force is released in the particular place. So, the P wave arrival surface earth of the surface and how it is integrated. So, this is how a source mechanism is generated. So, now if we recall that we have been discussing when the interpretation of the earthquake magnitude or estimating everything. So, I have shown that there was a diagram which is shown similar to this in the color, that is called as a source mechanism diagram. So, soon after the each earthquake report, people also release about what type of fault it is, what type of source mechanism associated. With respect to normal means normal fault, what how the beach ball, so the reverse fault how the beach ball, and then the thrust fault what is the beach ball, and then combination of this, okay, by changing this portion of energy they also release a, so which will help you to what type of source is it. So, let us see how the fault plane diagram for the normal fault. So, the seismogram located at point which the fault moving away where the pull and dilations are the first P wave motion. So, as you have seen that the normal faulting fault plane diagram of the normal faulting is given in, this is the normal fault and this is the fault plane. The white region represent which the first motion of dilation negative, and then the black region represents at the compression motion is the positive. So, you can see the compression portion on both sides and negative portion in the middle. So, this kind of fault source mechanism is called as a normal fault, okay, beach ball, okay, normal fault beach ball or source mechanism. So, the fault plane diagram for the thrust fault. So, where you have the only the seismogram has located point. So, where the moving will record push and compression, the faulting pattern will alternatively express as a compression dilation. So, the middle portion will have basically your compression portion, and outside you will have the dilation portion. So, this kind of fault plane solutions are given in the C, and the respective the fault plane diagram is beach ball diagram is given in the D. Okay. So, this, so like this each earthquake they will generate a beach ball diagram and they release that shows your source mechanism. So, you will have a this shape will be keep changing with respect to different earthquake. So, this one for example some people will release a beach ball only by locating a like this. So, this means only this much portion you have the positive, remaining portion is negative. So, some balls will be, so when the faults are behaving the reverse strike slip and kind of things, then this will be released like this. Okay. So, like this also they will release. So, you can see a different type of beach ball. So, even you can see sometime like this and then the like this. So, this will be sphere. So, you can see like this. So, it depends upon the fault orientation and the size of rupture and how much tensional force it released, this will be there. So, these data are obtained from the multiple seismometer and try to plot it in the, so the plan of the sphere, and then that plan is used to represent like this. Okay. This is how they will represent. So, this is the source mechanism concept which you need to understand. Okay. So, after understanding the source mechanism concept, the next is basically we will go to get a source model for the energy released by the tectonic plate. So, this is basically a simplest model, okay, which is used to tell how the seismic energy varies with the distance by is the function of your magnitude and distance. So, these are all the simplified model used historic times in the mostly on earthquake geotechnical engineering. So, people who deal with the earthquake and the geotechnical issues they use. These models continue to be used for the quick assessment when the data and time and other resources are limited. So, now there are very complicated models which you can use high end computing facility to simulate the data, but this is the simplified model one can use even in the software and normal regular computers also. Simplified models satisfy several requirements. They should offer conceptual clarity of the physical insight of the earthquake. That is why these models are still used in the check and quality of the data what you receive, how it matches kind of thing. They should be simple in physical description, in application permitting an analysis with the hand calculator or spreadsheet in many cases. So, the simplified fault source model and the planar source model. There are two type of models are there. First we will discuss about the fault point source model. Okay, point source model means here the source is assumed as a point. Okay, so as we described that, so this is the fault. Okay, so you may expect a rupture at this place. Okay, so when the fault is like 100 kilometer, so this rupture will take place maybe the 5 kilometer, depends upon the earthquake, 5 to several kilometers. So if the smaller earthquake, the lower will be the rupture. So in that case, if these earthquakes are occurring at 10 kilometer deep, and then so then this dimension, okay, whatever you are talking about here, 50 meter or 100 meter distance will be very small. So in that case, assuming the rupture as a point source is a logical rather than a aerial source. It is valid for the only a smaller magnitude kind of thing. That means the point source models are suitable for the only simple earthquakes. Okay, smaller earthquakes. The amount of energy transmitted to the location away from the source decrease with the distance from the source. So whatever energy generated at the source, as the energy travels on distance, the energy is consumed by the eating up traveling medium, part of the energy, and part of the energy basically transferred to the waveform. That waveform will reflect what is the energy. So as the distance, the energy will be reduced as the eating takes a time. Okay, this because the wavefront of the spread to the total energy along the wavefront equals to the source energy less the energy lost in the ground wave path. So by knowing this, at one particular place whatever energy you receive is basically the total energy minus energy lost by the traveling the distance. So the lost energy eat the ground, though very little. The eating is caused by the friction due to the relative movement of the soil particle during wave propagation. The energy transmitted to the ground surface is thus decrease further locations from the source. Okay, the energy can cause damage and destruction of the structures, lifelines and ground slope. So for this reason, it is necessary to estimate amount of energy released arrives at a particular place. The energy is responsible for your basically damage and ground destruction. So you should know what is the energy arrived at. So the rupture of tectonic fault start at one location, propagates over a fault entire area in time. Okay, so it starts here and then propagates in all the direction. Okay, so that is what we describe. So the forecasting dynamic fault rupture propagation. So the forecasting dynamic fault rupture propagation, so rather complex, okay, and therefore simplified models are used to explain this concept. The simplest of this model is a point source model. The reason why the earthquake source has been considered as a point, it is focus or hypocenter at a depth where the epicenter at the earthquake surface, or the fault area is small, the earthquake magnitude up to 5, the great source to site distance, lack of recording seismic station horizontally. So historically, so this small distance, okay, the larger distance and smaller rupture length can be called as a point, particularly magnitude up to 5. So 3 wavefront spherical wave when the earthquake occurs here. So when the earthquakes occurring here, so basically 3 wavefront starts and travel on different direction. So if you consider the sphere of the earth, okay, so the distance what it travels is basically ds. So this is the point focus, and surface projection is epicenter, which we know, and this is the site what you are expecting. The distance with this is ds, which is the hypocentral distance. So the usual method calculating the location of the earthquake hypocentral based on the relative arrival time of the longitudinal transverse wave at a set of at least 3 locations, which we have seen 2 lectures back. So the longitudinal seismic wave travels faster than the transverse wave, therefore there will be a time lag of delta t, which we have seen. P wave and S wave arrive, that time gap between these two are the very important. The time lag is essentially from the ground motion record. Let ds represented the straight line, okay, slant distance from the earth hypocenter recording on the earth surface. So the Vt and Vl denote velocities of the propagation of the transverse wave, which is the S wave, and the longitudinal wave, which is the P wave. The transverse wave like to distance Okay, so the time is equal to velocity into distance. As I told you that you get a velocity of the region is average value and distance you know. So, you get a time equal to distance into velocity. The arrive the site, the longitudinal waves take a ds. So, the VL to arrive, hence the measuring distance will be TW is the time lag between the this arrival time. The inverting the relationship, one arrives at a ds is equal to this time log and velocity 1 by velocity of the transverse wave minus 1 by velocity of the longitudinal wave. So, the distance ds can be estimated if the velocities are known on the interval of the length. So, the interval you can estimate from the recorded data, velocity from the regional average velocity can be estimated. By knowing this you can estimate a ds. So, this equation is strictly correct for a homogeneous ground without any ground wave fraction at a boundaries of the zone with the different wave propagation velocity. So, here we assume that the velocities are throughout the region is same. So, which is homogeneous. So, medium is only possible. So, earth interior is practically heterogeneous, therefore, the equation just first approximation of the calculation of the slant distance of the earth hypocentrus. Okay, this assumption you should remember. The wave propagation through earth interior causes mainly elastic small strain deformation, causes material damping, energy transformed into the heat by friction between the particle of their motion during the wave propagation is small amount, the amount less than 1% of energy transfer. So, the longitudinal transverse wave velocities are coupled by factor called Poisson ratio. So, the range of the for rock at depth greater than 1 kilometer is basically this is the Poisson ratio for the rock values. Okay, so, rock your Poisson values are there. So, on the deeper level basically you will have the rock materials only, not a soil material. So, this is the range. So, which is a very narrow range, the value variations are negligible. So, the point source model assumes that the wave front propagates from the source as a concentric sphere, and in any case the ground motion at hypocentral distance ds will be inversely proportional to the square root of the energy density. Okay, the energy square root of the energy density. So, that is basically the ED divided by E naught, the root, so approximately equal to 1 by E power kd ds and 4 pi into ds square. So, ds we know what it is. Okay. So, now we will see E naught is actually total energy released at earthquake at source, Ed is the energy density at the expected location, kd is average material damping coefficient which varies basically this is the amount. So, the Ambrasi and Saber then the term EDK determined by the both experimental and theoretical describe that the effect of material damping energy dissipation because of the internal friction. So, the term 4 pi d square the surface sphere of the radius ds basically describe the effect of radiation damping on the seismic energy dissipation with the distance ds to the source. So, the above equation basically we are converting to the sphere into 4 pi multiplication. The above equation the basic expression used to derive the almost attenuation relationship assume that the point source model it is strictly valid for the distance from the source where the body seismic wave dominated by the ground motion at a surface. This is the validity of this model described. So, at a distance greater than a few tens of kilometers okay, from the source okay, where the surface seismic wave Rayleigh wave appears to be surface predominant ground motion, the radiation damping may be proportional to ds of 0.5. Therefore, such circumstance the surface wave propagation in front will be the pi d. So, the Ambrasi Serblow 1998 showed that the average planar model fits better than the peak acceleration. So, this is about the point source model. So, further the people scientists worked for bringing out the planar source model where the source has been considered as a area okay, that is the planar source model. So, their calculations assume that the planar tectonic fault radiates the energy as a wave terrain uniformly in all direction. In a medium the average material damping the kd is the coefficient for the material damping. However, their model requires a knowledge of fault plane size, location of well as well altitude. So, the non-seismic zone information of that has been assumed by the engineering inferior. So, for example, earlier we have seen that the one location as a point projection epicentral distance hypocentral distance. When the area is this one then that area can be gridded as a different small grid and each grid you can get a d. Okay, so you can get a D at each, so D1, D2, D3, D4, then that D is linked here. So the total width is WF, total length is LF. This is basically the source area, and the grid portion is the function of this. Okay, that is the grid portion. So the known fault identified based on the past strong motion record, micro seismic activity observation and geological studies. The use of planar source model is not much complicated than the use of point source model. The model planar fault Serbulov, so 2004 used 4 Gauss point in integration scheme. The location of 4 integration point fault plane distance is actually given in the figure. So from this, the similar kind of energy loss variation integrated with the variation with the aerial dimension of the source, where you can see Di indicate the distance, and this L basically taking care, LF and WF taking care of the size of the planar source. So the ET is equal to E naught into WF by F. So by total energy released at earthquake source unit area at source, the LF is tectonic fault, WF is the tectonic width of the fault. So again the valid distance up to the source to site distance of few tens of kilometer, where the body wave seismic wave dominated ground motions at the surface. Greater distance where the surface wave dominated the ground motion distance, then this can be altered by looking at like this. Okay. So where you can see the influence of the, so the Di basically. Okay, you can see how this changes. Okay, that changes you have to observe when you use a surface wave. Okay. So that is what we discuss in this. So this kind of models we can use simply to show how the energy variation from that. E naught is actually energy at source. If you know the seismic moment and magnitude, then you can get source, and at a point how it varies with the time. So ET you can calculate. Okay. So people have used this model widely to accept how these models are vary with respect to the a particular application. Okay. So people have taken a typical record and try to work out model for that earthquake using the point and planar source and compare with the actual record to validate that model. So data from the case study comparison Ambresi et al. 2004, basic data given in the table. So he consider basically 3 earthquake Iran and then Monte Korea and Italy. So this is the earthquake details, so 88, 79, 80, and this is the magnitude of the earthquake. Okay, this is the magnitude of the earthquake MW, and this is the fault type what they use. So Ambresi et al. 2004 provide also the projection of the causative fault and earth surface, epicentral distance, hypocentral depth, fault plane inclination of horizontal, so that the above equation can be used effectively. So each earthquake listed table 1 horizontal ground acceleration were measured at a number different recording station at various distance from that. Ratio between the peak horizontal acceleration at 2 recording stations can be therefore calculated. If most remote recording stations are used as the reference, then the ratio of the station itself is a 1. The ratio of peak horizontal acceleration for the 3 ground motion listed in the table 1.1. So the ratio of the horizontal given in the figure. So the filled circle of square represent ratio source to site distance reported by Ambresi. Empty circle represents the calculated using the equation. The fault distance used to shortest distance among the recording station, just surface projection of fault. So you can see here the peak acceleration and source to site distance. One is from the epicentral distance model and then point source model, fault distance and then fault planar. So by the same earthquake you can see how these data are varies. You can also see for the another earthquake how these data are varies. You can see it has a variation with respect to point and planar source model. So this is for the another earthquake. So from analyzing this, so we can understand that so there is a good agreement between the predicted and the peak acceleration ratio based on the planar source model. Okay, that is the one thing. So the best fit ratios by thick dashed line calculated from the recorded peak acceleration using the fault distance as well as predicted peak acceleration based on the point source model. The best fit ratio calculated from the recorded peak acceleration using the epicentral distance. So it is possible to notice that number of outliner, the value of are significantly different for the best fit. So at the distance to source okay, distance greater than about 20 kilometer, particularly when the epicentral distance are used. You can see that when the distance are away from the distance, the variations are very large. So, this suggests that the use of empirical distance not always appropriate when considering the attenuation of peak ground acceleration. Okay. So, that means that so you should not use epicentral distance, okay, as a distance to represent your this one. So, the hypocentral distance are more logically good. Second, the use of basically point source models are not so effective when you are having the bigger magnitude. Basically, you can see these magnitudes are very large. Okay, you cannot use a point source model. Okay, so if you use the planar source model and hypocentral distance, that will be more effective to interpret a attenuation and model how the peak values or energy loss with respect to the distance. Basically, the energy is reflected in your strong motion record or seismic record in the form of amplitude and duration. So, these variations with the distance is actually reflected in the recorded data. So, if you want to capture that very accurately, you should use planar source model and hypocentral distance, not epicentral distance. In olden days, basically the use of epicentral distance are predominantly practiced. So, after this kind of research, people believed that, so it is proved that, okay, so basically use of epicentral distance is not appropriate to show the decay of earthquake or energy loss, okay, or the energy content in the earthquake. So, it is necessary to use hypocentral distance. Okay. So, particularly when the magnitudes are higher in the order. In case the magnitudes are lower, like less 5 and less, you can go for the point source model. If the magnitudes are higher in size, you should go to the aerial source model or planar source model. So, which we will be discussing in detail again coming in the what are the different simulation models are available, how these simulation models are used for simulating the synthetic ground motion which is required for the application. So, why we need synthetic ground motion? Basically, as I said that the India has seismic instrumentation after 1960 onwards. So, even the 1960 we have noticed that there is not many significant earthquakes are recorded at some region. But still you want to design your structure for a earthquake, because we do not know when earthquake going to occur, as we do not know what was the past history. So, if you want to design in those kind of region, you need to have the region specific simulation of ground motion, which considers here the source parameters, okay, source seismic moment and the quality factor and kappa, which is specific to region. So, if you have to account all those things, so you can you need to generate or simulate synthetically the earthquake motions. So, that is why the simulation of earthquake motions are very important for in the absence of the recorded data in the region. Okay, this is well practiced, particularly country like India, we have lack of proper earthquake recording. Okay, so hence the simulations are play a greater importance to get a predictive equation model as well as the timeicity data, which will be useful for analyzing the important structures like dams, nuclear power plant, tall structures and valuable structures kind of things, and also get a predictive equations on that. So, which we will be discussing in the next class. So, with this we will close today class. Okay, so I will thank you for watching this video. So, we will see you in the next class.